Hello and welcome to G Fun Facts Online. Today we're going on a journey, not through space, but through time, deep time. Imagine holding a piece of rock in your hand. But this isn't just any rock. It's a silent witness to the fiery birth of our planet, the slow dance of continents, and the very dawn of life itself. Sounds like science fiction, right? But it's not. It's the very real science of geochronology, the art of reading the unseen clocks hidden deep within ancient stones. This is how we decipher the immense, multi-billion-year history of Earth, and the stories these rocks tell will completely change how you see our world. So what exactly is geochronology? In simple terms, it's the scientific discipline dedicated to figuring out the age of rocks, minerals, and fossils. But it's so much more than just sticking a number on a stone. It's about building the entire timeline of our planet. By unlocking the ages of these materials, scientists can pinpoint the timing of cataclysmic volcanic eruptions, the rise and fall of massive mountain ranges, the opening and closing of entire oceans, and the dramatic climate shifts that have shaped Earth's history. This knowledge is the foundation for understanding everything from the evolution of life to where we find precious resources like gold and oil. It transforms our planet from a static sphere into a living, breathing, dynamic entity with a story that stretches back billions of years. For a long time, we could only guess at Earth's age. Early geologists developed what we call relative dating. The most basic principle is stratigraphy, which is a fancy word for a simple idea. In a stack of rock layers, the oldest stuff is at the bottom and the youngest is at the top. Simple but revolutionary. They could also use fossils, known as index fossils, to match up the ages of rock layers in different parts of the world. This allowed them to create a sequence, a what came first list of Earth's history. But it couldn't tell them when it happened. How many years ago was that dinosaur roaming around? They had no idea. The true revolution, the moment we went from a storybook to a calendar, came with the discovery of radioactivity. This discovery led to radiometric dating, the absolute heart of geochronology. Here's how it works, and it's incredibly clever. Certain elements in nature have unstable versions, or isotopes. Think of these as parent isotopes. Over time, these unstable parents predictably decay and transform into stable daughter isotopes. This decay happens at a perfectly constant, known rate, called the half-life. The half-life is the time it takes for half of the parent atoms in a sample to decay into daughter atoms. So if a mineral crystallizes from magma, it locks in a certain amount of these parent isotopes. By measuring the ratio of parent-to-daughter isotopes in that mineral today, and knowing the half-life, scientists can calculate exactly how much time has passed since that crystal formed. It's a perfect atomic clock, sealed within the rock. There are many of these atomic clocks. The gold standard, the one that gives us the most reliable and oldest dates, is uranium-lead dating. It's brilliant because it uses two separate decay chains happening in the same crystal, one from uranium-238 to lead-206, and another from uranium-235 to lead-207. Having two independent clocks that give the same result is a powerful cross-check. This method works best on a mineral called zircon. Zircon is amazing for this because when it crystallizes, its structure loves to incorporate uranium atoms, but it aggressively rejects lead. This means any lead found in a zircon crystal today is almost guaranteed to be the result of radioactive decay over billions of years. Other methods, like potassium-argon dating, are great for dating volcanic rocks, and techniques like luminescence dating can even tell us the last time a grain of sand was exposed to sunlight, which is incredibly useful for dating ancient sediments and archaeological sites. Okay, so we have the tools. Now, let's use them to visit the most ancient places on Earth. First stop, the remote wilderness of Canada's Northwest Territories. Here, we find the Akasta Gneiss Complex, home to the oldest known 9 intact rocks on our planet. Using that uranium-lead method on zircon crystals from this gneiss, scientists have dated these rocks to an astonishing 4.03 billion years old. But the age isn't the only amazing thing. The composition of this rock is very similar to our modern continental crust. This was a huge discovery. It was once thought the early Earth was covered in a uniform, dark basaltic crust, like our ocean floors. But the Acosta gneiss provides direct evidence that lighter, continental-style crust existed as far back as 4 billion years ago. This suggests that the processes that build continents, possibly even an early form of plate tectonics, were happening much earlier than we ever imagined. But the story gets even older. Let's travel now to the Jack Hills of Western Australia. Here we don't find intact ancient rocks, but something even more precious: tiny individual zircon crystals that have eroded out of even older parent rocks and been deposited in younger sandstone. The sandstone itself is about 3 billion years old, but the tiny zircons within it are far older. By dating these individual grains, scientists have found zircons that are up to 4.404 billion years old. Let that sink in. These are the oldest known pieces of our planet ever discovered. They formed a mere 150 million years after the Earth itself. These are literal time capsules from the Earth's infancy, an era we call the Hadean. And the secrets these time capsules hold are world-changing. First, their very existence tells us that by 4.4 billion years ago, the Earth had cooled enough from its initial molten state to form a solid crust. But here comes the bombshell. Scientists analyze the oxygen isotopes within these zircons. Their chemical signature doesn't match what you'd expect from a dry, fiery, volcanic world. Instead, their composition strongly suggests that the magma they formed from had interacted with liquid water. This is profound. It's our best evidence for the existence of oceans on Earth as early as 4.3 billion years ago. This completely rewrites the story of early Earth. The Hadean Eon wasn't necessarily the hellish landscape of popular imagination. Instead, the cool early Earth hypothesis suggests a planet that was far more temperate, a watery world with continents and oceans. And it gets even more tantalizing. More recent analysis has found tiny graphite inclusions in some zircons. The type of carbon in this graphite could be biogenic in origin, meaning it might be the fossilized remnant of the earliest life. While this is still hotly debated, it raises the mind-bending possibility that life may have emerged on our planet hundreds of millions of years earlier than our oldest fossils suggest. So what does this all mean? The dating of the Acosta gneiss and the Jack Hills zircons has fundamentally reshaped our understanding of Earth's earliest chapter. Geochronology isn't just about putting a date on a rock. It's about reconstructing a lost world. These ancient relics have provided concrete evidence that continental crust and liquid water oceans existed far earlier than we ever thought possible. This dramatically expands the window of time during which life could have arisen. It paints a picture of an early Earth that wasn't a barren, molten wasteland, but a dynamic, watery, and surprisingly habitable planet from its very beginning. The science of geochronology has unlocked the immense history of our planet, transforming silent stones into storytellers. And as we continue to refine our techniques and explore the most ancient corners of our world, you can be sure these time capsules still have many more secrets to reveal, continuing to shape our understanding of the incredible journey of the planet we call home. Thanks for listening to G Fun Facts Online.